Good afternoon, and thank you for attending this, the first in our Building Zero Carbon webinar series. The purpose of this series is to help develop the role of the UK construction industry in our efforts to deliver a net zero carbon economy by 2050. This initial session will cover a basic introduction and will explain how architecture can be used to deliver energy and carbon savings, whilst also providing reductions in capital expenditure. Upcoming events will go into further depth on particular topics, details of which we will briefly discuss at the end of today's session. I've been really taken aback by the level of interest in today's event, so I really do thank you all for taking the time out of your diaries to attend. The session is being recorded, and a link to this recording will be emailed to all attendees. So for those that don't know me, my name is Richard Tibenham. I'm the Director of Greenlite Building Physics. We're an independent building physics design consultancy, and we help architects and design teams deliver thermally comfortable and energy efficient buildings. Our services include summertime overheating risk analysis, architectural reviews, HVAC system sizing, daylight modelling, and building regulations compliance assessments. So a quick overview of the webinar today. The webinar will be about 45 minutes long with Q&A at the end. If you do have any questions, if you pop them into the Q&A box, we'll run through as many as we can at the end of the session. We'll outline the requirements of the RIBA 2030 challenge. I'll define what architectural efficiency is, and we'll discuss what the return on investment of architectural efficiency is. So before we commence, I'd just like to take a quick poll if we can, and I'd just like to find out how you found out about today's webinar, because that really helps us with our marketing activities for our next session. So if you could just quickly fill that out. See that you're filling that one in. I think we're about there. Oh, one or two more. Okay. Fine, I think that's about it. Thank you. Lovely. Okay. Okay, moving on. So to start off with the RIBA 2030 Climate Challenge. I'm not sure quite how many of you are familiar with this. It was established on 29th of June 2019 by RIBA, who voted to declare a environmental and climate emergency. RIBA chartered practices have been set the challenge of achieving the following reductions as soon as possible. Reduce operational energy demand by at least 75% before UK offsetting. Reduce embodied carbon by at least 50 to 70% before UK offsetting. Reduce potable water use by at least 40%. And achieve all core health and well-being targets. So this is the RIBA 2030 Climate Challenge. The areas that Greenlite Building Physics can help with are the operational energy demand aspects of the challenge, and also what RIBA refer to as best practice health metrics. And these include overheating, daylighting, and CO2 levels. CO2 levels being a proxy for indoor air quality in this case. So the challenge is often a case of balancing different factors, including operational energy demand against health metrics versus capital cost, for example. So I'm just going to take another poll. We won't be taking too many more polls. This is just the second. And I just want to get a feel for how many of you are keen to take up this RIBA challenge. So I'll just quickly launch that now. Will only be applicable to RIBA members, obviously. Okay. I've got a few of you that are keen, about 20% by the looks of it. Right, okay, I think we're that. Great, thank you. So we've got 21% who are very likely at the minute. So I think that's to be expected. Right, moving on. So let's start with asking, what does a sustainable building look like? I think in most cases, the first thing that comes into most people's head when you talk about sustainability is solar panels. Perhaps the discussion may move on to heat pumps, CHP units, and district heating. Now, all four of those systems all have something in common, and that is that they're all energy generation systems. They don't do anything to reduce the energy demand of a building, but they produce clean energy. To continue the conversation on, you may start to talk about insulation, and then as things carry on further, we'll start to introduce more terms into the mix. Now, I believe that a lot of these different systems and approaches are all reasonably well understood in isolation, but what I'd really like to talk about today is how these can all fit together in terms of architecture and building services as part of an efficient holistic system where architecture and building services both benefit one another. So this is a news article from the BBC from last year, and it cites a report which looks at reduction in fossil fuel usage between 2005 and 2019. And the conclusions of the report were that the equivalent of 95 terawatt hours was reduced due to the use of renewable energy systems during that period. But 133 terawatt hours were reduced due to efficiency measures. So there are efficiency measures like LED lighting, more efficient appliances, this type of thing, loft insulation and so on. And the report commented that the difference is that the glamorous renewables grab the headlines. The Cinderella field of energy efficiency, however, is often ignored or derided. So it's really the energy efficiency side of things that I'd like to look at more today, because it is a really influential area of delivering carbon reductions, and it doesn't really receive the level of attention that I think it should. So to start off with, I think it's important to make a clean distinction between what is an energy generation system and what are energy conservation measures. You'll note here that I've included passive solar heat gain within the energy generation side. But apart from that, I would say that there is generally a building services bias. These are generally energy generation systems which sit under the domain of a building service engineer. On the other side, on the energy conservation side, it's a bit more of a mix. You've got things like insulation and air tightness, which fit under an architectural domain. But you've also got things like mechanical ventilation with heat recovery units, earth pipes, LED lighting, which are building services. So I think there is a challenge definitely in bringing architects and building service engineers closer together to deliver a system which works well holistically. So we'll be looking at the fabric first approach today. I think most of you are probably fairly familiar with what that is, or at least maybe what you think it is. There has been an energy hierarchy that's been well understood for at least the last 10 years, I would say. And that hierarchy is be lean, use less energy, be clean, supply energy efficiently, and be green, use renewable energy. I think it's been well understood that in order to deliver a cost-effective building which performs well, that the first part of that exercise is to reduce the energy demand, to be lean. Then the be clean bit, that's bringing in efficient HVAC plants and so on, LED lighting, this sort of thing. And then just to top it off, it's the renewable inputs. Now, what we see in practice is more often than not, I would say, an inversion of these this hierarchy. We see the renewable energy systems given first priority, then consideration of the efficiency of supply, and then lastly the be lean element, the use less energy, which really covers fabric first. Now, there are reasons for this, which we can maybe go into a bit more detail on in the Q&A, but industry-wide we refer to this as greenwash, because generally you end up with buildings which appear green on the face of it, but don't perform particularly well in practice. So looking closer at the fabric first approach, which is covered by the use less energy part of the hierarchy, I think most of you are probably fairly familiar with things like insulation, air tightness, construction detailing, thermal mass, glazing specification, and build quality. But I would say, from my observations of what I see in the practice, the big area which I think could lend itself to a large improvement is what I refer to as architectural efficiency. So what do I mean by that exactly? What I define as architectural efficiency is aspects of a building's architecture which influences its operational energy demand, on-site energy generation, and indoor environmental quality. Okay, so we're talking about things like the layout and form of the building, the roof design, glazed area and orientation, and the solar shading strategy. So in terms of the layout and form, talking about things like the form factor, that's the surface area to volume ratio. The form factor affects the rate of conductive heat transfer from the building. The roof design, that can affect the maximum yield and the daily and annual energy generation profile from solar technologies. Glazing can affect a lot of things. It can affect the solar heat gains, conductive heat loss via the glazing, which is significantly higher than a section of opaque wall, daylight availability, and the risk of solar heat gain related overheating risks. In terms of solar shading, that can affect the overheating risk also, and daylight availability. So it's important to point out, looking at all of these factors, that they're all architectural issues, but they're not so subject to the material specifications so much, or the building services. Really is the architecture which defines the performance of all these attributes. So we'll be going through the webinar and looking more at how this affects the heating load, in this case, the building. Now in this case, we're looking at the heating load and how that can be improved in terms of a dwelling. But the same principles can equally be applied to an office, perhaps. And in an office, you'd probably be looking to optimize daylight availability, because artificial lighting is normally one of the higher fixed building service energy loads in that context. So the case study that we're looking at here was actually a project which came into the office a few weeks ago. And I thought it would be an interesting project to unpack for today's webinar, because either the client or the architect said that there is an air source heat pump and PV panels proposed, with ideally the air source heat pump powered by the PV panels so far as is practicable. Now, obviously, that there is some interest in providing energy efficiency, whether that's for cost saving or for green reasons. And I wanted to really demonstrate how the architecture performs against the renewable generation. So I've modeled this building up using IES virtual environment software. And here's a quick rundown of the attributes that I've included in the model. So we've got some reasonably good U values, 0.2 for walls, floors 0.225 and so on. Double glazing at 1.6, so we're not going as far as triple glazing in this case. Pretty airtight, 3 meters cubed on the air tightness there. HVAC system is going to be a wet radiator circuit running off the heat pump. Likewise, the hot water will run via a 300 litre cylinder, also using the heat pump. And it's going to be naturally ventilated with mechanical extract fans. On the roof, we've included just shy of 14 meters square of PV, which tops up to a 1.52 kilowatt peak array. So just to note that this specification is somewhat similar to the Future Home Standard. It's not fully been agreed yet, so I don't quite know what it's going to include, but it's probably going to be in this sort of area. So if we take a look at the annual energy demand profile for the building, we have months, January to December, across the bottom of the chart. And up the side, we have the running average energy demand. That's in terms of kilowatt hours. It's quantified in every 30 minutes. So I've built up the model, I've broken it down, and I've looked at what the energy demand is every 30 minutes. I've taken an average of that data. So we can see that the space heating energy demand from the air source heat pump provides the vast bulk of the energy demand for the building. Shown in orange is the hot water demand, that's comparatively low. Lighting energy also fairly low. And equipment energy demand covers any plug-in appliance, washing machines, cookers, this sort of thing. You can see that there are some negative values across the bottom of the graph there, and that's the effect of the PV generation reducing that bottom line. However, it is important to note that even during the summer, it is still incurring positive energy demand. The PV isn't generating enough to run the whole building. So in this case, it's the energy demand for the building is about 44.36 kilowatt hours per metre square. And the RIBA 2030 challenge target for 2030 is between 0 and 35 kilowatt hours. So we will need to look to improve this building in order to deliver on that target. So if we now look at the client's desire to have the heat pump run by the PV cells, you can see here in red the energy demand to run the space heating load for the heat pump. In orange is the hot water demand. In blue we can see the PV yield. So that's comparatively low compared to the energy demand that the heat pump is drawing. And if we subtract that heat pump load from the PV generation, we end up with this profile here. So you can see that the PV cells are only capable of providing enough heat to run the heat pump between June and mid-September. And that coincides with when the radiators are turned off. So it's only really capable of delivering on the hot water demand here. Throughout the heating season, it doesn't deliver enough to run that heat pump. So I've calculated this to equate to about 34% of the year if you have some battery storage, and about 24% without battery storage. So it's not really performing particularly well. You're just delivering that energy autonomy during the summertime season. Now, there are considerations to bear in mind with that, which are to do with the seasonal carbon factor of the electric grid, and that's something that we can look into during our next webinar. So how can we improve on this? Perhaps we could introduce some further solar heat gain to reduce these heating loads, because that's the primary. I've just got a hand raised here by Kin Chung. If you can just pop your questions in the Q&A box, Kin, we'll run through everything at the end. Thank you. So what I've done is I've basically taken that wing of the building which projects out to the south elevation, and I've just swung it around to the end there. So I've reduced the west-facing glazing. That is to reduce overheating risks. I've increased the area of south-facing glazing, and I've also introduced some brise soleil to reduce the potential for summertime overheating. Now, this change alone reduces the space heating demand by 11%. And which isn't a huge amount, but if you bear it in mind with local planning policies, perhaps, which ask for a 10% energy reduction, you can deliver that simply by changing the shape of the building. Now, I should point out here, I'm not intending that this is an architectural masterpiece. I've simply swung this around just for argument's sake, just so that there's no question marks over additional volume to the building or floor space or anything like that. Now, theoretically, the cost uplift for this should be zero, because we've not added any additional envelope area to the building to add on to construction costs, but you're achieving that energy demand reduction for zero cost effectively. So if we look at an annual energy balance of this now improved geometry, we can see where heat is coming from and where it's going. So the primary energy input into the building is still the radiator circuit. That's the radiator heat gain shown in red. Solar heat gains shown in orange there. Internal heat gains from people and equipment, lighting, that type of thing, that's shown in grey. And although it's not a heat gain as such, I've just shown the PV generation in black, just so you get an idea of the proportionality. You can see that during the winter especially, the PV array generation is tiny compared to the space heating energy demand. So even if you were to double or triple the PV array, it would still be very small compared to the amount of heat that the building requires. In terms of the heat losses from the building, we've got the conductive heat losses. So that's conductive heat loss through the walls, the floor, the roof, the windows. And also the ventilation losses, bearing in mind that it is a naturally ventilated building. Infiltration, it was fairly airtight from what you recall. That's fairly minimal. So if we look at this wintertime season, which is the primary area of interest in terms of decarbonisation, big challenge is how we provide this low carbon heat. If we break this down, we can see that the radiator heating consumes about is responsible for 59% of the heat gain. Solar heat gains, internal heat gains are fairly equal, about 19%. You're only getting 2% off the PV array. In terms of heat losses, it's almost a 50-50 split between conductive loss and ventilation losses. So, question is, how can I reduce these losses? If we want to bring down the energy demand of the building, we need to reduce the heat loss from the building. I think, as I explained, simply throwing more PV at the problem will not create that much difference. The big problem here is that the building loses too much heat. So perhaps you can look at insulation, a mechanical ventilation heat recovery unit, and a high level of airtightness. So that's what I've done. I've modified the building, and now it accounts for what a more passive house standard like attributes. Got improve the U values, passive house type levels, windows are now triple glazed, air tightness is less than 1, same heating system, but now the ventilation is via a mechanical heat recovery unit. PV array remains unchanged. So we now have 2 geometry options, both with this improved specification. And I'd like to know how these 2 geometry variants compare now that the construction has been upgraded. So the question is, by how much will the heating demand be reduced? So I'm going to take another poll here, and I'll just get your feedback on what you think. What reduction in space heating energy demand do you think the improved geometry can offer now that both variants have an upgraded specification? So if you'd like to have a think about that, I shall launch that. Still have a few of you pondering the looks of it. Right. One or two more. Oh, saw some coming in. I think we're more or less there. Okay, I'm going to share this one with you because I think the results are quite interesting. So hopefully you can see that. The majority of you think that the reduction in space heating energy demand will be between 20 and 30% for the improved geometry, and it's not a huge amount of difference between 10 and 20%. Okay, so let's have a look. Here's the two graphs. The blue graph here shows the space heating energy demand for the proposed geometry. The grey graph shows the space heating energy demand for the improved geometry. Reduction 57.6%. So you can reduce the space heating energy demand by nearly 60% simply by changing the shape of the building. So here's the breakdown. With the proposed geometry, with the triple glazing and all the upgrades, looking at a space heating energy demand of 3,548 kilowatt hours per year. If we change the geometry, we can more than half that to just above 1,500. And I think what's also interesting is if you were to take the improved geometry and specify it with double glazing instead of triple glazing, you would still achieve a 40% betterment over the proposed geometry with triple glazing. So clearly there's cost savings available here simply by refining the shape of the building. And we'll go into what those cost savings look like towards the end of the webinar. So now that we've got this improved geometry, we'll take a look at the energy demand, the energy balance now. You can see it's a lot flatter throughout the year. So we'll take a look again at this period, 1st of January through 31st of March. We've now got 29% heat gain from the direct solar heat gains, and internal gains contribute 34%. So rather than the radiators contributing 60% of the load, we're now exceeding that simply through solar gains and internal gains. PV generation has gone up to nearly 4% thanks to having just a lower overall energy demand, and we've reduced the radiator component of this down to only 33%. So you can see the effect of that improvement of the geometry to yield greater passive solar heat gain really has a very pronounced impact on the radiator energy demand. Likewise, on the losses side of the equation, still got about a 50-50 balance between mechanical ventilation heat loss and the conductive heat loss. So if we were looking to improve on this further, we'd maybe looking to raise the efficiency of that ventilation system. So in terms of the RIBA 2030 target, we're now hitting 26.8 kilowatt hours per metre square, so well within the RIBA target. However, if we do want to get down towards this zero target, we will need to do more. And you will find that as you get closer and closer to that 0 point, the demands on the architecture become more and more critical, to the extent that when you are hitting zero, the architecture really is quite extreme. And I've been carrying out some analysis work into this, and it does involve very large areas of south-facing glazing. So that is a topic of conversation that we can go into on a future webinar. So another way of looking at this is how much PV does it require to run the building throughout the year. So we can see here that with the baseline geometry, the proposed geometry, you would need over 300 metres square of PV to run the building in January, and around 275 metres square in December. We don't have that much on the roof of the building. In fact, the roof isn't even big enough to sustain that area. So the maximum that you can fit physically on that roof is around about 70 meters square. So theoretically, if you were to line the whole roof with PV, we could run the building autonomously between about April and mid-September. So during that spring, summer, early autumn period. If we now compare that to the improved geometry, not only does the building require a lot less energy, there's also more south-facing roof area available. So in this case, we'd only need about 200, I'll say only, but you'd need 225 meters square of PV to run the building autonomously in January. The maximum you can fit on that roof is about 88 meters square. But that makes the difference. You have this big hop up between PV demand in January and in February, as you get more solar heat gain in February and the temperatures are that bit higher. So theoretically, we could run the improved geometry from February through to mid-October. And that adds an additional 3 months of potential energy autonomy. Now, although that may seem somewhat extreme now, as we transition closer towards a zero carbon economy, but by 2050, these issues will become more and more critical. We'll have electric vehicles that need powering. People will be trading energy in real time based on supply and demand. And having that availability to export energy during periods of high demand will become increasingly lucrative. So all the buildings that we build today will probably still be standing by 2050. So my argument is that these type of things should be considered at this design stage. At the moment, just for comparative purposes, we have about 14 meters square on the building. So you can see that that doesn't even cover the energy demand during July. So breaking this down in terms of pounds and pence, what does this look like? If we take the proposed geometry with the upgraded specification, so that's the passive house-like spec, let's assume that's our baseline. So we've got 0 additional capital cost and there's 0 additional operational cost. We could substitute the triple glazing in this case and swap it out for double glazing. That'd save you about £7,400. But your energy demands would go up by about £85 per year. We could remove the PV array. That'd save you about £4,500 in capital cost, but your operational costs would rise by £584 per year. And we could substitute the air source heat pump for a gas boiler. It would save £2,800 on the build, but we'd also increase operational cost by £95 a year. Now, if we look at the improved geometry, just the improved geometry alone, nothing else, would save you an additional £286 a year in running costs. We could swap the triple glazing for double glazing, saving £7,400 on the build. You would still be saving £199 a year compared to the baseline. You could remove the PV array. You might decide that you want to do that at a later stage. You'd save £4,500 on the build. You'd only incur £5 additional running costs compared to the baseline per year. And you could substitute the air source heat pump for a gas boiler, save £2,800 on the build. You'd still be saving £226 per year compared to the baseline. So although these operational costs are still fairly low in layman's terms, reductions in capital costs are really quite attractive when you're looking at substituting triple glazing perhaps. And obviously this is just a notional example. You could improve on these figures if you wanted to further. So if we take a worked example of what the payback period looks like, if you were to appoint us to look at improving the architectural efficiency of the building, let's assume that you're appointed for 4 hours based on our fee of £75 an hour. It's £360 including VAT. Pay £360, and you wouldn't reduce your capital cost any if you're just going along with those changes, and you'd save £286 per year in your operational cost. So in year 1, you wouldn't quite cover our expenditures, but then from year 2 on, you'd be saving £286 per year. If we look at substituting the double glazing, you would save £2,040 in that first year because you've saved on that capital cost, and then moving forward, you'd save nearly £200 a year on your running costs. So you're looking at ROIs of nearly 2,000% here in terms of the substitution of the triple glazing. Likewise, the PV array could save over £4,000 at the build stage. In year 2 onwards, you're only incurring an additional £5 on your energy costs because you're benefiting from those cost savings made available through the improved geometry. Obviously, if you do want to put the PV on at a later stage, then that's something that you can do, but you've got the foundations right by reducing the energy demand in the first place. Finally, if we look at the gas boiler substitution, save £2,654 in that first year, and then moving forward, you'd still be saving £226 per year. So if we look at this graphically, and I'll come into the end of the webinar now. Some of you are losing the world. We can see that passive architecture and this architectural efficiency is really cheap to employ. You can get big benefits from very low capital cost. The capital cost is really just improving the design side of things. It needn't necessarily cost any more in terms of capital cost. In fact, the capital cost could even be reduced if you're clever about things. So in terms of payback, it actually outperforms the payback from a PV array up to about year 14. After year 14, the PV array does provide a superior payback. In terms of the heat heat pumps don't actually offer that much cost benefit without the RHI, the renewable heat incentive. It's really the inclusion of that renewable heat incentive which improves the attractiveness so that you can pay off the asset within about 7 years, rather than even without the RHI, the heat pump in this context would not have paid itself off after 15 years. And a heat pump will probably be looking to expire after about 15 years. So it won't have paid itself off within its service life. Moving forward, as I mentioned earlier, I think that the cost difference between on-peak and off-peak electricity will broaden. On-peak electricity at periods of high demand will become more expensive, and off-peak electricity will probably get more expensive as well, but not so much so. So people will be increasingly looking to optimize the time of use that they use energy, and that has a big impact on storage and things like that, which we can talk about in a future webinar. The other thing to think about, as I mentioned earlier, is the longevity of these systems. PV array may last 30 years, possibly a bit more. PV array, you're probably looking at about a 15-year life expectancy. The passive architecture, that lasts for the longevity of the building. So you're paying a fairly small amount to lock in these solar heat gains and then provide that benefit over the lifetime of the building. So how can this help you? Firstly, it can ease compliance with performance targets, things like the building regs, the future home standard, which will be coming out shortly, BREEAM, and Passive House. Can deliver project cost savings to your clients without compromising on the performance, as we've run through. And it can deliver ROIs which outperform renewable energy installations in many cases. It can future-proof buildings with improved medium and long-term financial value. So what I mean by that is you can build in that capacity to expand the PV array perhaps, and it'll, you know, including more south-facing roof, for example. You can build in more solar heat gain so that you're locking in those benefits for the long term. And I believe that should improve the financial value of that asset as energy efficiency becomes of increasing value. It can also obviously satisfy the RIBA challenge, which is the main topic that we're going through today. So that can help gain industry recognition and awards and so on. And probably more importantly than anything else, it can help address climate change, which is what all of this is about, and pressure on the energy grid, which will inevitably be coming under increased pressure as things move forward. So in terms of recommendations, low energy buildings begin with sympathetic architecture. And what I mean by that is without getting the architecture right, you will really struggle to deliver an energy efficient building. I've worked on enough projects now to realize that if the architecture isn't correct at the planning stage, you will be fighting an uphill battle to get that building to work well. Bolt-on gadgets are not a substitute for good design. We should not be looking to just substitute things like passive solar heat gain, insulation, fabric first and so on with just tack on measures like heat pumps and PV. As I've demonstrated in the webinar today, the PV yield is really comparatively quite low by comparison to space heating demand in this case. And I think it's really things like the feed-in tariff which have warped the approach to this with the because that's counterbalance the financial arguments for some of these things. But I think looking towards the long term, it's really important to build in energy demand reduction in priority to energy generation. Don't approach new build schemes with a retrofit design philosophy. It's the same type of thing really. Don't just build a building the way that you otherwise would do and then tack on heat pumps and PV cells as if you were dealing with a retrofit project. I think in terms of retrofit, your options are limited. You can't rotate the building around 90 degrees. You can't change the roof design, for example, that easily. Whereas at the new build stage, you've really got a fairly blank sheet and you can optimize the aspects that we've been through today. Obviously, it's less critical for low performance buildings. So naturally ventilated, lower levels of insulation. But as we increasingly look to target low and zero net energy demand, these architectural efficiency aspects become more and more critical. So question to yourself, what other methods can deliver a 60% reduction in space heating loads whilst incurring only negligible impact on the project budget? There's not many, and I'd argue that there's none. And finally, the greatest cost benefits are available at the pre-planning stage. Really need to get this stuff right before it goes in for planning. Once it's gone in for planning, normally the aesthetic and the form of the building is fixed. So at that stage, it becomes quite difficult to come back and modify these things. You can't just approach energy consultant and say, we've got it through planning, it's ready to go, it's on site in 2 months' time, what can you do for us? Because the available options are really pretty limited. You need to get in very early. So that nearly wraps things up. I'm just going to hold one final poll, and I will ask if I can. So what I'd like to know is, given what we've been through today, will the information shown today change the way that you approach projects with low energy aspirations? So if you just want to fill out that is the final poll. Well, that's quite reassuring. Anyone that has said no is because they already employ these principles. So, that's good to know. All right, I think we're there with that one. Great, thank you for that. I'll just share those results so you can just check them out. So 40% of you have said yes, 20% already apply these principles, no one said no, 30% no context, and 8% are not applicable. So that's quite reassuring. So moving on, we're nearly done now. We'll get on to the Q&A. So how Greenlite can help with these aspects is we do offer a 30-minute free design review. We'll go through your project, we'll point out any obvious errors. We've literally done hundreds of projects, and we're wading through all this data in depth on a regular basis. So I've got a good understanding of how buildings perform theoretically. So we can use that knowledge to just avoid some common pitfalls like large areas or west-facing glazing, for example. They can lead to overheating risks, and that's just one example. We do also hold a design review clinic, and that is on the first Friday of every month. So we get maybe 3 or 4 architects around a table, all bring in our architect or bring in our designs, and we run through everything collectively. So it's a collective learning exercise. So that's how we can help. I will pop out an email tomorrow with a link. So if you want to take up that free 30-minute design review offer, you can book in via our calendar. So finally, just a very quick look at our next session, which will be into, oops, I've actually put January 2020 there, it means January 21 actually. But in this session, what we're looking at is the scalability of net zero carbon approaches. And what we were looking at is largely based around this graph. This graph shows UK natural gas demand in blue and the electrical grid capacity in red. As you can see, the natural gas demand dwarfs the available capacity of the electrical grid, particularly in the winter. So we will be looking at how we can bring these wintertime loads across to the electrical grid, and at the same time introduce additional load from electric vehicles and decarbonise the grid at the same time. It's a huge challenge, and I think probably one that a lot of people underestimate. So that's a bit of an insight into the next webinar. But that wraps things up for today. So we'll I think we're just just gone over 45 minutes. So now we'll open things up to Q&A. So Nikki, if you want to come into the conversation now, and we'll run through some questions.
Richard, I'm just actually replying to a few of the chats there, so we've got those out of the way. But hello everybody. So we've got a question from Amar Katab. I've seen a project in America where they use deciduous trees to shade the building in the summer and maximise sunlight during the winter. Are you aware of any examples in the UK?
Yes, to some extent. Yeah, green shading systems, really great idea. I've actually got one growing up the front of my house. So in my case, I'm simply growing a wisteria. And so yeah, they create leafy shading during the winter, during the summer. And they also produce a degree of evaporative cooling effect. So they're good in principle, they're natural obviously. You do have to wait for the plants to grow. And there's also a maintenance cost, which puts off a lot of commercial clients. For example, the maintenance costs probably outweigh the cost of running an air conditioning system, which is why a lot of people don't bother. But I'm all for them. I think they're a really nice idea, and they can improve the aesthetic of the building. You do also have things like green facades, which maybe don't provide the shading effect so much, but do provide that evaporative cooling effect. So there's a handful of projects like that, especially down in London, but it is more where the budgets are available for that type of thing. So I can't think of one off the top of my head where they've used deciduous trees, but I'm sure that you can find a few examples if you Google it.
Okay, so Bob asks, can efficient architecture be applied to retrofit projects?
Right, so obviously with retrofit, your hands are tied a lot more in terms of what you can do with the building. You can't, for instance, rotate it around 180 degrees. And that is the whole argument for getting buildings right in the first place. Once a building is built, it is generally immovable. So if we are building buildings for now, which are still going to be stood in 2050, even if they're not carbon neutral now, we need to think about how we're going to transition them to carbon neutrality over the next 30 years. So in terms of retrofit, it depends how far you want to go with it, really. If it's a case of taking the roof off the building, for example, you could consider how that new roof design will work in terms of PV yield, for example. But I'd say largely you've got your hands tied in what you can do because the building's already built.
Okay, so Luke asks, do you have any interest in your advice or services from planners? Often planning requests comments on architectural appearance, respect of context can thwart the architectural efficiency. Yeah,
no, absolutely. I'd say that I am always trying to get planners to the table, and by and large, I would say not all of them, but by and large, they are not particularly interested and completely lack the knowledge to deal with these sort of aspects. Now, I do fully appreciate that planners are under a lot of strain. They've been pulled in a lot of different directions, but as we've been through today, you can't fix these buildings by simply just tacking on additional green measures. It needs to be an integrated approach which uses the architecture. The architecture is the first step of the process. So I will agree, if you're going down a road of trying to argue a position in terms of the architectural design of the building, which favours the efficiency of the building, but then the architects, the planners want you to do something completely different, that is a conversation to be had. But I think at least if you can point them towards this webinar, it will be made available online, you can at least get them to understand the justification for why you're taking a certain approach. But yeah, the top and bottom of it is that the planners need to come to the table on this, and it's going to take more than me to do that.
Okay, and one's just popped in from Anjana. Yep. What are more efficient for renewable energy generation, biomass boilers, heat pumps, or CHPs?
Well, if you're talking about efficiency, it's going to be the heat pump, I would say, out of that, but I'm not sure if that's quite what you're getting at. I think you need to be careful in terms of what factor it is you're actually trying to optimize, whether it's CO2 or energy demand, and what type of energy for that matter. In the biomass boiler will be using wood fuel, a heat pump will be using electricity. So, I mean, a biomass boiler will be less than 100% efficient. A heat pump could be up to, well, a lot more than 100%. I think 300 or 400%. CHP units. For a long time, CHP units and heat pumps have been sort of levying for priority. I think here in the UK, in London, CHP units were used a lot in hotels, student accommodation, these sort of buildings that have high domestic hot water demand, especially throughout the year. Now, the problem that's introduced is that they incur very high NOx levels. So you've got all these mini power stations around London kicking out very high levels of NOx, and that is reducing the urban air quality. So there's been a big clampdown on the use of CHPs in London, and now things are moving more towards heat pumps. So I think without going on too long, I think there's more issues to look at in that question than just efficiency, and maybe that's something that we can hold a future webinar on.
Okay, the last one from Brian.
Mm-hmm.
Can we get you in front of RTPI conferences?
Not at the moment, but I am certainly open to that. If you'd like to pop me an email, Brian, and we can get something hooked up. But yeah, no, I'd be more than happy to contribute to this agenda as far as possible. So yeah, pop me an email, Brian.
Okay, Brian goes on to say CAMS ran some CPD for LA, T and CPO, they welcomed them.
Absolutely, yeah. No, pop me the details, and I would be more than happy to do that, Brian. So thanks for that.
I think that's all questions.
That's the lot. Thank you, Nikki. Wonderful, great. Well, I hope you've all enjoyed the session today. I hope it's been worthwhile. We will be holding the next one in January, and we'll pop an email out tomorrow just with a quick questionnaire just to see how things went, so that hopefully we can improve the next event. But that's it for now, so thank you very much.